A particle p moves along the x-axis. At time t seconds, where t is greater than or equal to 0, the displacement x meters of p from the origin is given by this equation. And then for part A, we're trying to work out the times when p is instantaneously at rest. Okay, so what that means is, for part A, we're trying to work out when the velocity is 0. So, if I expand out the displacement equation, a half t to the 4 minus t cubed plus a half t squared. To get velocity, we have to differentiate displacement. So dx dt would be 2t cubed minus 3t squared plus t. And if v is 0, then that means that 2t cubed minus 3t squared plus t is 0. So this is what we're then going to be solving. So factorize out t. And then we can factorize the quadratic that we have here. So we're looking for two numbers that times together to give a times c, which is 2 times 1. A times c is 2. And we're looking for two numbers, the same two numbers, that add together to give b, so minus 3. Those two numbers would be minus 2, minus 1. So then we can rewrite the quadratic as 2t squared minus 2t minus t plus 1. So we're rewriting the minus 3t as this. And then we can factorize each half. So take out 2t from the first half, that's a common factor there. And from the second half, we take out minus 1, because then we end up with the same bracket, which is what we want. T minus 1 is a common factor of this term and this term, so take that out, and we're left with t minus 1, 2t minus 1. So this becomes 2t minus 1, t minus 1 equals 0. So we get t is 0, 2t minus 1 is 0, and t minus 1 is 0. So our 3 times are 0. This one gives a half, and this one gives 1 when you rearrange. So t is 0, t is a half, t is 1. Okay, for part B, find the total distance traveled by p in the time interval of 0 to 2 seconds. So x is equal to a half t squared minus 2t plus 1. So I'll write that down over here. X is a half t squared minus 2t plus 1. And then we can rewrite this as, so we can factorize what we have here. That's the same thing as t minus 1 squared. And that's useful because now we can sketch this graph. So I can sketch a graph of displacement against time. So this is a quartic. There's two roots. We can get them from t squared is 0 and t minus 1 squared is 0. So this one gives t is 0. This, if you square root both sides, you get t is equal to 1 when you rearrange. And they're both repeated roots. Because we have t squared, t minus 1 squared, that means we have repeated roots, which means that for our quartic, those parts of the curve would not go through the axis, they would just touch the axis like this, or like this. Now this is a positive quartic. We can tell because we have a half t squared times t squared, which would be half t to the 4, which is positive. And a positive quartic looks like this as opposed to that. Okay, so our graph looks like this, where this is the origin, t is 0, and then we also have t is 1, which will be this point here. Alright, and then from the previous part, we worked out where the velocity is 0. We worked out when the particle is instantaneously at rest. That's when v is 0. V is 0 at these times here. T is 0, t is a half, t is 1. Velocity is 0 when the gradient of this graph is 0, because velocity is the gradient of a displacement time graph. Gradient is 0 here, here, and here. So the 0 we have already, the 1 we have already, and the half must therefore be this point here. So this point is a half. So these three purple points are the points where our velocity is 0. and they are also the points when our particle changes direction. So the particle is going forwards, then it goes back, then it goes forwards again. So for this question, we're trying to work out the distance traveled by p in the interval of 0 to 2 seconds. So let's now put 2 on this as well. I'll put that in I'll use a different color for that, so this is 2. Okay, so now that we have our graph, this should become much easier to work out. The total distance traveled would be the distance from here to this point, so we're going forwards by a certain distance. We then go back by the exact same distance, so we double whatever this x value is. And then we go forward to this point, we go forward by whatever distance this is. So we need to work out what x is equal to when t is equal to a half. So when t is equal to a half, x is equal to, we can put that into this equation here, and we end up with 1 over 32. Okay, so then drawing that on our graph, this point here is 1 over 32. And then this point, when we put in t is equal to 2, what does that give us? So put in t is equal to 2 into this equation, and we end up with 2. So that point is 2. Okay, so we're moving forwards by 1 over 32 meters, backwards by 1 over 32 meters, and then forwards again by 2 meters. So the total distance traveled would be 1 over 32 forwards, and then backwards, and then forwards again. This is 33 over 16, or 2.06 meters. And now for part C. So, show that p will never move along the negative x-axis. Okay, so if p will never move along the negative x-axis, that means that x will always be positive. What is x equal to? X is, I'll use the factorized form. That will help us explain this. So this is what x is equal to. Well, if we look at the components of this equation, t squared, it's a square, something squared. This must always be positive. Same thing with t minus 1 squared. That must also always be positive. Well, that will therefore mean, if we're timesing half, which is positive, by t squared, which is positive, by t minus 1 squared, also positive, this whole thing is positive, so x must be also positive. And that's it. That will be your answer for part C.